into cloud server. Nobody else. It's just you.
No, there's a few. A few keen beans.
Oh, there you go. Hello, everybody.
Hi, everyone.
See everybody coming in?
Yeah.
That's good. Some familiar names there. Hello, thanks for joining us again.
Hi. I'm amazed you keep coming back.
I'm not.
It's all his charm, obviously. It's not mine. It's my beauty, his charm. Yeah.
Yeah, well, I don't have much of that. Never mind.
Hello, everyone. It's so great to see you all.
Yeah, it's good.
Hopefully the IT... Oh, we've got Alison Bradley from the United Kingdom.
Hey, Ali.
Hey, Ali. How are you? Who's the furthest? Who's come further than the United Kingdom? Hmm?
Anybody from Mars? No?
Well, in your case, it probably is. Yeah. Yeah. We wouldn't miss it for anything, aren't you, sweet Kim? Thank you. It's really nice. I know we can't see you, and you only get to see us, but it's really lovely to know you're all out there. So thank you.
Especially those of you who've heard all this before. This is nearly a new talk tonight. There's so much happening in this field.
It's a fast-moving,
very fast-moving field.
Mm-hmm.
Almost bursting.
Excellent. So, I'm curious to know: do people have dinner while they're watching this? Have they had it before, or are they having it afterwards? I guess it depends what time zone you're on, but. It's always tricky knowing what time to set something like this. And yeah.
Must be morning tea time in the UK.
Yeah. Ali will be on. Oh no, I was going to say. No. Excellent. We've got Bev and Bill. Hi, Cheryl.
That's great.
David. There's a few Davids there.
That's because they're in alphabetical order.
They are in alphabetical order. It's nice to see some people from Macquarie University. And just as we're going through, if you haven't joined us before, if you have any questions throughout the talk, there's a Q&A button at the bottom of the screen. That's the best place to ask your question. In fact, I've seen one just come up now. And should you be able to see other people? No. No, we've got about 200 people joining us tonight. If we put 200 people on a screen, you might find that you're all a bit pea-sized. So it's just Fred. I'll jump off in a little while. By the way, my name is Marnie Ogg. I'm the director of Dark Sky Traveller. His name's Fred Watson. What are you the director of?
Nothing.
Oh yeah, you're the astronomer at large.
That's right, yeah. But I might just mention at this juncture, to those of you who've already joined us, that this would not have happened without Marnie. Marnie is very much the brains behind all this. The idea of cosmic relief was something we both dreamed up, but Marnie made it happen. I can't do that.
So we're on the run. We're learning as we go. We've had two successful webinars already. A few little glitches with IT because there's so many people on board. But as always, if you miss it tonight, if you drop out, if you get tired, fall asleep on the lounge, then it'll be online on Dark Sky Traveller in the next couple of days, and you can watch it, catch up television in the next few days. So we've still got a few minutes.
We do. Lots of people coming in.
It's doing pretty well. Yeah. Oh, I will turn my emails off. That was an email coming through, but I just like to leave it open while people are trying to get on in case you have any issues.
In case they say, help, I can't see anything.
Yeah. Yeah. Excellent. So now I've lost you. It'd be awful to hang up on you all, wouldn't it?
Yeah, it's so easy to do as well.
John Latanzio, Fred, from Melbourne.
Oh, no pressure.
No.
Hi, John. Oh, dear. So when professors of astrophysics join your talks, then you know you're in real trouble when they're astronomy talks.
Oh, we've got Nick Lom, former...
There you go.
Sydney Observatory
or directors of observatories.
Yeah.
I might just give up now.
Yeah. Should we let them do it?
Yeah, let them do it. That's right.
Okay, excellent. There's lots of familiar names here, and it's really nice. You got fantastic.
Hi, Richard. Richard agrees there.
Yeah.
Very senior person in Macquarie University.
Yeah. Fantastic. Well, Fred, it's 7:30. Will we kick it off on time?
Kick off on time, or do you want to give?
Let me just see if there's any questions here about. There's a few good questions coming through there already. So if people have got their questions lined up.
Fantastic question there.
Yeah.
Really.
Yeah, I'll get that
That's
one.
Awesome, that one.
People can't see what you're pointing at, but I can.
No.
So yeah.
You've got 4 more to go, 3 more to go, 2 more to go.
We got 100.
Before we've got 100.
We had over 200 people register for tonight, which is really
okay. There's 100. 100 come up. Thank you, everybody. Thank you for making this so well worthwhile. It's great to see you all. Let me just scroll down for a minute just to see. There you go. A few people we know on that list.
Like Fred's boss. That's not me for a change.
No, there are some good friends on.
Oh no, Hawaiian shirt tonight. Yes, that's true.
No, I've gone back to the pink.
Actually, this shirt is from Hawaii.
It is, yes. It came from Hawaii. That's right. It's not what you call a Hawaiian shirt, but it came from the factory outlet in Lahaina in Maui. There you go. See, I know where my shirts come from.
A few professors of astrophysics have said, "Don't worry, Fred, you'll be fine." You'll be fine.
Oh, somebody's got
Pinot Noir.
Noir.
Oh, lucky you.
Good on
excellent.
You, who said that? Oh,
someone said Fred's getting uglier. That's not very nice.
No, it's all right. I know.
It's true, but it's maybe it's against my beauty.
Look,
this is like a stand-up comedy show, isn't it?
To the person who told me I was getting uglier, John, you all know that the beauty is in the music, much of which you have shared with me over the years. Thank you very much.
Hi, Tony Law. That's very nice of you to send a message to us from Swan Hill. Excellent. I bet you have some beautiful clear skies out there at the moment. And wouldn't miss this for quids. Oh, well, someone must be paying you.
I miss it for dollars. But no,
all right, here comes Mandu.
Yeah, so he wants to be part of the action, and he could do the talk. He's doing the talk tonight. There you go.
He can't handle not being at the centre of attention.
No. That's fair enough.
All right, Fred, I think we should kick it off.
All right, so let's kick it off. It's 7:33 in the evening. You can look after Mandy. I'll see you in a moment. So I'm just going to start up. So whilst Fred makes his way into the magic box room, thank you again for joining us, and thank you for being part of this wacky idea of webinars. But we do appreciate you being there and hope you enjoy tonight. Fred Watson and Fast Radio Bursts. Take it away. Nearly there. Okay, I'm assuming that since you're smiling, Marnie, that you're seeing what you meant to see on the screen. Good, that's a thumbs up. All right, so thank you again, everybody. Thank you to all of you who've signed in for this. It's wonderful to have you. I'm very thrilled that COVID-19 has not stopped our outreach activities. It's a really great opportunity, and I think this might be something that becomes very much part of normal life over the next few years, not because of COVID-19 necessarily, but just because it's good stuff. So thanks again to Dark Sky Traveller, that's Marnie of course, for hosting this third Cosmic Relief webinar, which is on a topic that is very, very fast moving, as we mentioned earlier. In fact, at the end of this talk, I'm going to bring you some news that only came out today, thanks to my colleague in the business, Stuart Ryder, who keeps me informed in these things. So, fast and loose, well, it's as good a title as any. I might just explain that graphic that you're looking at now by a gentleman called Pitris, that's his name, is of a thing called a magnetar. and I'll explain what magnetars are as we go along. But by the end of the talk, you will find you'll know all about these things, and at least you'll know as much as I do, which is really only scratching the surface. But never mind, they're very important. But this, of course, is an artist's impression, but you can get the impression that they are highly, highly magnetic. So the fast radio burst mystery. There's the usual disclaimer. I'm the nation's astronomer at large, which is a great privilege. I work for that department, and as I've said many times before, the Department of Industry, Science, Energy and Resources consists of 3,000 grown-ups and 1 astronomer. But I do have some very much appreciated university affiliations too. Let me start by putting up this beautiful painting by Cal Piquet, who's in Western Australia. And clearly this is very much a classic example of our Aboriginal art.
Have you shared your screen?
Yeah, can you not see it?
No.
Marnie says she can't see the screen sharing.
You just see you.
You're not supposed to be able to just see me, you're supposed to be able to see a screen. Shall I do it again? Let's just,
try again, yeah.
Let me just stop that. Sorry, folks. I'm stopping sharing. Okay, what can you see now?
Try it, yeah.
Yep.
Some saying they can, some say they can't.
Okay, let's try again. And here we go to where we got to. Tell me if you can see that, Marnie.
I've got you. You need to play the screen.
It is playing.
That's it. Got it.
You got it? Yeah. Excellent. Okay, here's Mandu coming to help me, which is great. He's got a favourite spot underneath a chair in the study, and that's where he is now. So let me begin by drawing your attention to this beautiful portrait. It gives me an opportunity, of course, to acknowledge the traditional owners of our country. And this is a very, I guess, a bittersweet day in the history of the nation. 250 years ago today was when Captain Cook arrived in Botany Bay, changing the history of Australia. But our Aboriginal brothers and sisters here in this country have been looking at the sky for tens of thousands of years, perhaps the oldest astronomers in the world. And so it's always fitting to acknowledge the traditional owners and to pay our respects, as we always do, to elders past, present and emerging. This picture, of course, many of you will recognize. It is the emu in the sky, and shown beautifully against the background of the Milky Way. That's the artist's view of it. The astrophotographer's view of it is like this. This is a beautiful image by Tony Caswell, which was one of the, I think he was one of the finalists in the 2019 David Maley Awards. And you might remember, if you were watching 2 shows ago, I did talk about those awards. But it shows the Milky Way pretty well the way you would see it a bit later tonight, if you look out to the northeast. The Milky Way rising with those dark, I mean, you need to be in a dark place, I have to say, not in the city, centre of a city, although we can see the Milky Way from here in Terry Hills. But get out into the country and you can see the emu rising over the the southeastern, I beg your pardon, not the northeastern, southeastern horizon. And I've sketched in where the emu's head is. It's not a very good drawing there. That dark patch, which is the emu's head, is what we call the coal sack, a name given to it by John Herschel in the early 19th century. The coal sack is a dark, dusty nebula. And in fact, those dust lanes in the Milky Way are what form that beautiful Aboriginal constellation of the emu. This image also shows one of the, or two of the other reasons why we are privileged in our vantage point in the Southern Hemisphere. The 2 Magellanic Clouds, the large cloud at the top, on the right-hand side, the small cloud beneath it. These are our 2 nearest dwarf galaxies of any size. And they lead me, along with the Milky Way, with the Southern Cross there. I don't know whether you spotted it, but there's a better view here. that is the cross in the middle. This is another 2019 David Malin Awards finalist by Peter Ward, a lovely image with the emu's head in the middle there. But it leads me to a prologue to this talk, which is to set the scene in terms of why we can now talk about things like fast radio bursts. And that's because Australian astronomy has some infrastructure which a few years ago, a decade or so ago, we didn't have, but that has all come together to allow us to understand these very, very brief and fleeting phenomena from deep space. So this prologue, beg your pardon, is about our vantage point on the universe. Why is it special to be where we are, especially in a time like this? I love this graphic, which shows the observatories in the world that are closed because of the present emergency, the COVID-19 emergency. And all the red dots are telescopes that are closed, and you can see that includes the Anglo-Australian telescope on the right there. It will open again for business as soon as is possible. I'm hoping it won't be too long. But all the major observatories in northern Chile, the telescopes on Mauna Kea in Hawaii, all the southwestern US observatories, the South African Large Telescope, Southern African Large Telescope, I think is its proper name, and the telescopes in the Canary Islands, all closed. The one that you might spot on the far left of your screen that is open is Pan-STARRS, a robotic telescope at the summit of Haleakala. And just in case any of you have ever wondered, that is the summit of Haleakala in an indigenous Hawaiian painting. It's a favourite spot of mine. It's got a Pan-STARRS telescope on the top, which is open for business because it's watching for near-Earth asteroids, objects that might collide with us here on Earth. So that's the present situation. Very brief note. But for us in Australia, our vantage point has certain advantages. And one of them is kind of what I've hinted about already, the latitude advantage. Where we are looking from, there are some of the most important objects in the entire sky. The center of our galaxy, for example, in the constellation of Sagittarius, the two Magellanic Clouds that I just mentioned, those beautiful dust clouds and dust lanes, the coal sack near the Southern Cross, which itself, of course, is an iconic constellation, but also the two largest and most prominent globular star clusters in the sky. All these are really important things, giving us a bit of a lead for our quest to understand the universe from here in Australia. Now, those things I've just mentioned can be seen anywhere in the Southern Hemisphere. But one thing we also have here is a longitude advantage, in that if you think about where the land masses are at our latitude, you've got mostly ocean, and Australia sits between Southern Africa and South America, and there are telescopes in both those continents. So our telescopes kind of fill a gap, which is important if you've got what we call transient objects, things that come and go. But perhaps more especially things like supernovae, exploding stars, whose brightness rises very quickly and then fades slowly. It's not quite so true with the objects we're going to talk about tonight when I get onto this topic in about a fortnight, but that you get the idea that we have an advantage because of that. We also have relatively stable atmospheric conditions, not quite as stable as in northern Chile, but pretty good, which is why I'm showing you our biggest optical telescope there in the middle of the screen. We've got dark skies and also calling it the most radio quiet site on Earth. There might be others nearly as good, but there is a place which is very important to our story where there is virtually no radio interference that is human-made at all. Here's the Anglo-Australian telescope, the largest optical telescope on Australian soil, 46 years old this year, and it's still doing world-class science. That's partly because of its instrumentation, but also because it's in a good place. And its real strength is its dark sky. In the Warrumbungle mountain range, as this beautiful picture by one of my colleagues, Angel Lopez Sanchez, showing the Milky Way there with the trees silhouetted jet black against the sky. which tells you that what you're seeing there is the natural brightness of the night sky, because there's no artificial light anywhere near. However, Siding Spring is not the only place in the southern hemisphere where there are dark skies. And here's another place which is very important to us. This is the summit of Cerro Paranal in northern Chile, where the 4 telescopes of the Very Large Telescope, the European Southern Observatory's Very Large Telescopes, are sited. Each one of those large enclosures contains a telescope with a mirror 8.2 meters in diameter, more than twice the size of our Anglo-Australian telescope. And as you will know, in astronomy, size is everything when it comes to gathering the light from faint objects, or indeed the radio signals from faint objects, as I'll get to in a minute. So we now have this wonderful strategic partnership between Australia and the European Southern Observatory. Goes for 10 years from its inception in 2017, and it gives Australian astronomers access to what really are the world's finest suite of Southern Hemisphere optical telescopes. They are fantastic. And that, as it says below, is important in the fast radio burst story. It's part of the tale. Let me move very quickly, while we're talking about our vantage point on the sky, to the other important aspect of the FRB story, and that is our radio observatories. Because Australia is part of a project, and a very important part of a project, to build what will be the biggest telescope in the world. It's not a visible light telescope, it's a radio telescope. Here's an artist's impression of what part of it might look like when it's finished, and I'll explain what you're seeing there in a minute. But let me tell you that this is a major collaboration, and of course here in Australia, CSIRO, through CSIRO Astronomy and Space Science is the one of the main movers and shakers in the venture. But SKA, the Square Kilometre Array, called that because it will eventually one day have a collecting area not measured in meters but in millions of square meters. 1 million square meters is 1 square kilometre, hence the name of this facility. And it is a worldwide facility. As of very recently, it now has 14 partners because of the entry of the Swiss to the partnership. This is a slightly old slide that doesn't show everyone on there. But what you can see is that the facilities are in Australia, Southern Africa, and there's one in the United Kingdom, which I'll get to in a moment. So a major venture with, we hope, the first signals coming into the final square kilometre, or something we call SKA1, the first stage of the SKA towards the end of the 2020s. Let me take you to where it is. It is situated at something called the Murchison Radioastronomy Observatory, which is about 350 kilometres northeast of Geraldton in Western Australia. And you can get there either by road or rather more conveniently by air. And I was very fortunate a little bit more than a year ago to find a seat on the plane that was taking some very eminent people, including the chief scientist, Alan Finkel, David Todi, the then, and I think he still is, chair of the CSIRO board, were visiting the observatory. And so the astronomer at large scrounged a lift with them, and I got to get the VIP treatment with the air traffic. So what have you got? We have a site where Australian radio astronomy facilities are being built. As I said, the world's quietest radio site, no mobile phones there, and not much else either that emits radio radiation. In fact, the site, like our visible light observatory site at Siding Spring, is protected by a dark sky region. In fact, the Arana dark sky region, it's actually not called that anymore, but that's how it started off. There is a radio quiet zone centered on the Murchison Radioastronomy Observatory, which extends out to provide a 520 kilometre diameter region. And once again, paying acknowledgement to the traditional owners. This is the country of the Wajiri Yamaji people who are working with the Australian government and the other agencies involved to make this a very, very special part of Australia. This is one of the facilities there, and I'm showing this picture because it reminds me that one of the Wadjuri elders, a man whose name you might very well know, Ernie Dingo described these radio antennas as being like wildflowers growing out of the desert floor, a lovely analogue. And these are very large dishes, in fact. This is one of the precursor arrays to the Square Kilometre Array. What you're seeing here is something called ASCAP, the Australian Square Kilometre Array Pathfinder. You don't need to worry about the details of frequencies, but you can tell that you've got 12-metre antennas there. They're big, and there are 36 of them in the Murchison Observatory. I want to show you a close-up of what there is at the focus of one of these, because that's what makes this facility rather special for the quest for fast radio bursts. So these dishes have at their focus, and that's at the apex of that triangular structure there, not just a single radio receiver, which is what most of the radio telescopes in the world have, but something called a PAF, P-A-F, a phased array feed. And you can probably, depends how much resolution you've got on your screen, I can just see it. That circular disc that you can see at the focus of the telescope is not just a single disc, it is kind of broken up into pixels, basically, because this is essentially a radio frequency image sensor. It has effectively 36 pixels. Now that's not quite like your 1000 megapixels or whatever you've got on your optical detectors for astronomy, but it does give this telescope a significant advantage in the fast radio burst story, as we'll see in a minute. This is the visit that I was telling you about. There's the chief scientist, Alan Finkel, with Anthony Schinkel, who's one of the CSIRO scientists involved with this, showing the kind of mosaic structure of those phased array feeds. And there, we also on the tour got to see some of the other facilities. This one in particular is much more closely related to what the final Square Kilometre Array will look like, actually, than the ASCAP Pathfinder. And this is the, as I said, a second precursor telescope. This is the Murchison Wide Field Array, operated by, well, the operation is led by Curtin University in Perth, directed by Melanie Johnson Hollett, who was there on this tour. Basically, you've got 4,096 of these strange little coat hangers, which is basically a low frequency radio telescope. They're arranged in tiles, as you can see there. Each tile has, I can't remember how many, should be able to do this in my head. Anyway, there are 16 by 16. Yeah, that's the number. 16 by 16 of these things, and then large numbers of the tiles. What's crucial about this is that there are no moving parts. These things are electronically steered. And that is the clever aspect of this. It's a low frequency telescope that isn't pointed around like one of the ASCAP antennas. It is steered electronically. And as I've said there, a field of view of 30 degrees, that's colossal. 30 degrees, remember that the moon is half a degree in diameter. Think of that, then you've got 60 moon widths in the field of view of that telescope, and that makes it very, very powerful. I'll make mention of the MWA again in a minute, but let me just show you this, which is actually one of the prototype versions of the final Square Kilometre Array. Itself will consist of 130,000 antennas, and it covers that low frequency region. You can see it's called SKA1 low. The one is basically the first stage study. Low refers to low frequency. Distributed over huge distances, once again in little tiles of several hundred of these things. What I'd like to draw your attention to is the data rate from this, 10 times the total global internet traffic. And that, of course, means you've got to have some very clever data handling techniques. This picture, taken once again on that visit late in 2018, shows what a more advanced version of these Christmas tree antennas will look like. I might just point out that that one is screwed down to a metal screen. It's actually a kind of grid, but that's a sort of earthing screen. rather than being attached to concrete bases like the ones you can now see on the left. Those concrete bases were government surplus manhole cover surrounds from the British Telecom, I think. They fell off a truck or something like that. Actually, they didn't fall off a truck. I think they were quite expensive. And they were designed to anchor down these antennas. But I think there's been a more effective and rather cheaper way of doing it, as shown in that more recent prototype there on the right. And of course, the other thing that you need for a project like this is this mega computation needed to turn the signals into science. I mentioned Southern Africa. There is a precursor in South Africa, in the High Karoo there. It is called Meerkat. It's in the Northern Cape province, and itself has 64 13.5 meter diameter antennas, a little bit like the ASCAP array, but actually covering an even higher frequency range. So that is what makes SKA mid, the mid-frequency component of the Square Kilometre Array. I love the name of this precursor because CAT, the KAT, is actually an acronym for the Karoo Array Telescope. It's in the High Karoo of South Africa. But when it was proposed, I think they were going to have 20 antennas in CAT, but the government said, we'll give you more money and you can build more, extending it to 64 antennas. And of course, that then becomes more cat, which in Afrikaans is meerkat. So it's not just a cute animal, it's also a great name for an array of telescopes. And the final component of the SKA is the headquarters, which are not far from Manchester at the Jodrell Bank Radio Telescope, an iconic telescope in British history. I have to say that I grew up not very far from Manchester, and I never saw it looking like this. The sky was never that colour. Never mind, that's all right. It's a great facility, and there's fantastic work being done there. We know that they too are in COVID-19 lockdown at the moment, but we had a message yesterday from the Director General, Phil Diamond, somebody I know, who is the Director General of the SKA, saying that they hope that people will be able to return to the facility very soon. What will it do? One final slide about the SKA, pretty well everything. It will be able to observe the whole history of the universe, from the dark ages before the first stars formed to galaxies in modern times, investigating gas flows around galaxies. And I love the notion, which I might have mentioned before in one of these cosmic relief talks, the notion that it will have the sensitivity to detect an airport radar at 50 light years. So that's one for the extraterrestrial search lobby, the SETI brigade, I can put it that way. Right, that's the prologue. Now we get to the talk itself, which is, I think, one of the most exciting things going on in astronomy at the moment. This, of course, is an artist's impression of a fast radio burst hitting a telescope, in fact, an Australian telescope. So what are they? What are these things all about? There's a lovely bit of history attached to this, and it starts with perhaps the most iconic radio telescope here in Australia at Parkes. I always think it's one of the most lovely telescope settings in the world, after Siding Spring, of course. It's got this, I always think it looks as though the telescope just grew there, which has lovely, lovely echoes of Ernie Dingo's comment about ASCAP. It's been running for a very long time, 1960, I think it might have been, or even before that. It's been going for a while, as I'm sure somebody will tell us. Okay, so back in the early 2000s, this gentleman, whose name is Duncan Lorimer, he's a Scotsman, but he works at West Virginia University in the USA. In 2006, actually, I've got 2007 there, but I think the work they did 2006, the paper was published in 2007. They were looking through archival data from the Parkes dish. Like all big telescopes, you don't just get your information from an instrument like that and then throw it away. It goes into an archive. And that archive, after 1 or 2 years, depending on the proprietary period, is released publicly. So anybody can have access to it. And it's a way of utilizing the world's telescopes to to the best advantage. And in fact, that is becoming more and more important as the equipment that we have, both in optical and radio astronomy, as it gets capable of gathering data on ever larger numbers of objects. So the Parkes archive was being looked at by Duncan and his colleagues, and what they were looking for was pulsars. And in fact, the Parkes radio telescope has a very strong history of pulsar observations. In fact, they found the first one, pulsating bursts of radiation. So I've said there, brief clock-like bursts of radiation that come from rapidly spinning neutron stars. And just to unpack that, what I mean is essentially clock-like clicks, up to 1,000 per second actually, which for good reason are known as millisecond pulsars. What is happening there? Well, you've got an object that is about the size of a city, maybe 10, 20 kilometers in diameter, with more than the mass of the sun compressed into it. So it is incredibly dense. In fact, the only thing that stops it from collapsing to a black hole is the outward pressure of the neutrons on each other, which is why it's called a neutron star. Here's an artist's impression of a neutron star. They tend to spin, sometimes, as you've just heard, very rapidly, but more especially, we know that they have very strong magnetic fields around them on their surface. Once again, an artist's impression designed to show you what they might look like. And the result of that is that at their poles, the fields are so strong that they essentially focus beams of radiation outwards. And if the object is spinning, then you can get this sort of lighthouse beam effect. If we are in the right line of sight, if you've got this spin taking place, we will see flashes of radiation, which has made Mandu sneeze there. You must be astonished at this. And so that's why these things are called pulsars. They were, they were first discovered actually by Dame Jocelyn Bell Burnell. So not at Parkes, but the very early work was being done at Parkes. The discovery was I think in Cambridge. So the pulsars are reasonably well understood. The first one discovered in 1967. We've known about them for more than 50 years, and we understand that they're pulses of radiation that come from these rapidly spinning stars. Duncan was trawling through the archival data, but he found something else quite different, which puzzled him a lot. And in fact, he found something that in some ways mimics a pulsar flash, but there was only one, a single burst of very high intensity radio radiation that came and lasted essentially, I've said there, 5 milliseconds, and then disappeared and was never seen again. That was very interesting. It's now called the Lorimer burst, as you can see, and the details of that paper that it was published in November 2007 is down on the left there, sorry, the right. But what I want to tell you about is what made this special. So that strange diagram has two parts to it. And if you look in the upper right-hand corner, you can see a kind of crooked trace, a noisy looking trace with a pulse, a peak towards the left-hand end. And that is essentially the pulse of radiation. That is the blast of radio waves that we're seeing. But that particular diagram at the upper left there is just at one radio frequency, one single frequency. And if you do what we do in visible light astronomy, which is to spread light out into its component frequencies, we usually talk about wavelength, but they're more or less the same thing. They're just one inverted by the speed of light is the other. If you think about it as color, in spectroscopy, in optical astronomy, we disperse light into its spectrum colors, and we can tell lots of detail from that by this information that is presented. Radio astronomers do things slightly differently, and especially when you have a pulse of radiation like this, yes, you can break it up into its component colors. By that I mean the frequencies, but you can also plot it against time if it's a pulse like this one. And across the bottom there you can see time in seconds. So this brief half millisecond millisecond pulse, if you spread it out in color or frequency, then it shows this, what we call a dispersion. It's not all at one time, it's spread out in time. So up at the top there is the higher frequency, which you might think of as blue light if you're following the analog. Down at the bottom is low frequency, which you might think of as red light. And this pulse sweeps through those different frequencies in a period of less than half a second. But what is significant about this is that that sweeping comes about, it's something radio astronomers are very familiar with because this happens with pulsars as well. It comes about when something has traveled through a lot of space. And that's because we know that space is not empty, not completely empty. There are electrons, for example, in deep space, and they essentially slow down the lower frequencies. That's putting it very simply, but that's what's happened. So the more of a dispersion you get, the sort of shallower the angle that beam makes as it reaches the Earth, the more electron clouds you've gone through, and hence the greater distance you're looking at. So this was the key that made this interesting. That slope of that line tells you that it's come a long way, that you're looking at something that came from great distances. So they were well baffled by this. There is a quirk to this story, which I can't resist telling you. It took an unusual turn because what happened was people trawled back looking through the data at Parkes to try and find other similar phenomena. And sure enough, they found some. They found that they've been going on since 1998. And because they could see several of these, they gave them a name. They were called peritons. And a periton is a mythological creature, as it says there, invented by an Argentinian author, Jorge Luis Borges, back in 1957. I haven't read the book that these things appeared in, but apparently they look like this. This is a periton, according to Wikipedia anyway. It's clearly green. It is a winged stag-like creature with, very interesting faculties. So these peritons were essentially discovered. The name was given to these radio bursts that were discovered in the Parkes data. But something curious about these things, their arrival seemed to be linked to the rotation of the Earth, rather than having some sort of cosmic origin. Things that happen in deep space don't care about the Earth, so they pop in at any time. These were always coming in at round about the same time of day. And so people thought of nuclear tests and aircraft signals, all kinds of different things. And there was a suspicion that it might be something quite local. And I've talked to John Sarkisian at Parkes about this in detail. It's a lovely story, and I haven't time to tell you the whole details of it. But eventually they were traced to the Parkes lunchroom microwave oven, because it turned out it's not just switching it on or switching it off or using it. What you have to do is to cook your meal, your lunch or whatever, and press the door open button while it's still cooking. And that gives you a periton in the telescope. You get this dispersion, this frequency drop, which might be due to, maybe it's due, I think John Sarkisian suggested this, that the magnetron inside the enclosed cavity of the microwave, suddenly that enclosed cavity has got bigger because the door is moving away from it. So you get this drop in frequency. Lovely, lovely stuff, and part of the folklore now of radio astronomy. John Reynolds and John Sarkisian owned up to this very quickly, and I think the astronomical community reacted not with scorn or anything remotely like it, but with sympathy and understanding, and well done on eliminating something that could have fooled us for a long time. However, other people were finding these fast radio bursts. And then something happened basically I can't see because my screen's blocking off the name of that FRB. It's 12 something or other, I can't remember the details, which was the first repeating FRB. In fact, if I go to the next slide, No, I can't do it. No, never mind, never mind. 12, whatever it is, 12 and 11 something, I think, if I remember rightly. That is in the data, archival data, again, from what was then the world's biggest single-dish radio telescope at Arecibo in Puerto Rico, which, as you can see, is basically a depression in the ground with a 300-meter diameter radio dish in it. There is now a bigger one called FAST, which is in China, and that is 0.5 kilometre in diameter, which I think is working pretty effectively from what I hear. But the Arecibo data showed not just several single burst fast radio bursts, but also one that repeated. It was the first repeating fast radio burst. And so what that did was immediately told you that one of the things that had been suspected was probably not the case, at least for this one. And that was objects blowing themselves to pieces at the end of their lives, maybe exploding neutron stars or something like that, putting out vast quantities of energy. So whatever this was, that was something different from a single burst, fast radio burst. These are images of that object or that event, or that repeated event, taken by a number of different telescopes. The Gemini telescope, there are 2 of them in Hawaii and in northern Chile, 8-meter telescopes, and Spitzer, which is an infrared telescope, and the Hubble Space Telescope. I don't want you to worry too much about this, but if you look at, for example, look at the 2 Gemini pictures and the upper part of that, the 2 middle ones. What you can see is a blob, which is, I think, probably a star in our own galaxy. You can see a very faint ellipse, so you might not be able to, but there is an ellipse there, which is the uncertainty region for the fast radio burst. And off in one corner of the ellipse is a fuzzy blob, which is a galaxy. And that turns out to be a dwarf galaxy 3 billion light years away. So we are looking at things that have come a long way. And the suspicion from that information on the screen there is that this event was taking place in the outskirts of a fairly unassuming galaxy, not in the center of it, as you might expect for energetic processes. It was at that stage, I guess, where things kind of really took off in the FRB story. And I've called it the new era of fast radio burst research. And I've got a picture there, an artist's impression again from the Osgrav group at Swinburne, of ASCAP, the Australian Square Kilometre Array Pathfinder, which it turns out is very good at finding fast radio bursts. And part of the reason for that is because of these paths that I told you about, the phased area, the phased array feeds. And you can see that this diagram, maybe, I hope you can see it, has some bright flashes there with superimposed on them the sort of pixel pattern of the paths. That means that you don't have to be pointing in exactly the right direction to pick up one of these things, because your telescope has a field of view, which is actually, if I remember rightly, it was 30 or 40 times the diameter of the moon, that area of field. And the other thing you can do with an array like ASCAP is, instead of using all the telescopes, that array of 36 telescopes, instead of pointing them all in exactly the same direction, you can make them point in slightly different directions to give a kind of fly's eye effect. And that widens your view. And in fact, it meant that the telescope was looking at 1/3 1,000 times the size of the full moon as it was scanning the sky. That might have been the ABC an hour too early. Never mind.